All right, so this is the follow-up video from the review session. So there will be things I will reference that, and I'll scroll back up through, that is absolutely just from the review session. That was Sunday from 4 to 6 p.m. So if you haven't watched that video, some of these may not make sense. I'm also not going to go in order on these. So this is a set of questions that I was given. So this actual question at the very bottom says, how do we work from percent composition to mass? So how do we work from percent composition to mass? If I didn't make that one clear, that was actually, I did an example problem of that. So scrolling back through here. So there was a question I did that just said a sample contains 68% vanadium. The rest is oxygen. What is the empirical formula? So this question here is percent composition, and then it's going to empirical formula. So this one does that idea. So you start off with the 68% vanadium. You solve for the amount of oxygen. You take both of these to go from grams to moles. You have mole amounts. You go ahead and divide by the smallest number there, and then you work to get things into whole number ratios. So that one is something you can do if you begin with percent composition. So as far as working it from percent composition to mass, the thing is that we don't, I guess if you wanted to go just to mass and stop, then realize that your percent composition is really in a percent by mass. So when we say that something is 68% vanadium, that is 68% of the mass. So if I wanted to say that I had a 100-gram sample, I would just use percentages. So I could take my 0.68 times 100 grams to then get my 68 grams. If I had a different sample size, I would do that same idea. So if I had something like a 15.3 gram sample, I would just multiply that by 0.68%, or pardon me, by 0.68. So this is one of those that if you've ever done like things are on sale and how much is something worth, this is that same general principle. So hopefully that one helps clear up that idea of percent by mass and what we can do with it. But really that original problem where we start with percent by mass and we work to empirical formula is what is going to be more common. I'm actually going to go from the bottom to the top. Do we know the effective nuclear charge equation? No. And actually, most classes did not cover effective nuclear charge. So effective nuclear charge is interesting. This actually would have been back in earlier chapter 4. It's interesting, but we are not covering it. So this effective nuclear charge, that short answer is just no. It's got an equation to it, but we've actually never tested on that. This next one, can you have double bonds all around phosphorus? So this is going to go back to looking at phosphate. And so I want to go back. Let's make that smaller. And take a look at what happens. Here's our phosphate stuff. So this is the structure that we ended on. So to remind folks, we did go ahead and end on this one. Well, again, so this one has resonance. So even though I am showing it with a double bond only in one location, we could do the bond order for this molecule and remind us that really in real life, all of these bonds, all bonds are 1 1/4 in real life. But the question's about formal charge. So we ended here. So this particular oxygen has 6 valence electrons, has 2 electrons that are being shared, has 4 electrons all to itself, that's 0. Then we have the phosphorus, where the phosphorus brought 5 valence electrons to the party. I'm not scrolling back to a periodic table, but you can certainly take a look at a periodic table to find those valence electrons. And then it is sharing 5 electrons in all of those bonds. It has no electrons all to itself. That's also 0. And then I can go ahead and grab all of these, all the remaining oxygens look the same. So this oxygen has 6 valence electrons. It has 1 bond to it, or 1 electron it's sharing in a bond, and 6 electrons all to itself for a -1 charge. So essentially I've got a -1 here, a -1 here, and a -1 here. So as the question was pointing out, I have 2 elements that are 0, and I have 3 elements that are -1. So that's where we actually left off. The question then was asking, well, why don't we just go ahead and draw double bonds all the way around phosphate? So why don't we just go for it? And phosphorus can handle it, which is true, and just give it a whole bunch of double bonds. So let's just go ahead and double check. So here's my oxygen. It looks just like the one we started with. 6 valence electrons, 2 electrons from bonds, 4 electrons all to itself. That's 0. And then all of those oxygens look the same. So the person's point was that we'd have lots and lots of negative ones, or lots and lots of zeros, which is true. But let's go ahead and do phosphorus. This is 5 valence electrons. It now has 8 from those bonds. No electrons all to itself. That's a -3. So what we wind up with now is these are zeros all the way around. And then phosphorus actually has this -3 on it. So the whole idea of formal charge and of dealing with Lewis structures is something that I didn't mention in the review. But the goal is to basically evenly spread the electrons if we can. Because the whole idea of having Lewis structures and having these molecules together is these are covalent molecules. They're sharing electrons. And we should actually have those electrons as spread out as possible. So even though, again, this one that I drew that's on the right is a valid Lewis structure, it's valid. The thing is that has a very high negative charge to it. So that's got our phosphorus basically hoarding a lot of the electrons towards itself. So this is not terribly likely since these are covalent molecules and they ought to be sharing. The other thing to keep in mind is phosphorus is less electronegative than oxygen. Oh dear, where is my periodic table? Now I want it. So phosphorus is hanging out on the periodic table, and phosphorus is in fact less electronegative than oxygen. So since phosphorus is here and oxygen is here, putting a giant -3 charge on phosphorus also doesn't make as much sense because oxygen is closer to fluorine. It should be the thing that wants to have that greater electron density. So in real life, oxygen should be carrying a negative charge if it can. So because it's got that greater electronegativity, especially in comparison to phosphorus. So when we're doing these various Lewis structures, while I know they're two-dimensional and trying to deal with things like resonance, this is not always the best way. We are trying to demonstrate everything that we can and can accurately in this diagram. And so in here, it's this new one is less likely for various reasons. So this one over here on the right is valid, but not best. This one over here on the left is what we would refer to as the best Lewis structure. Well, once I drew, oh dear, -3 charge. Should look like this one over here without all the scribbles around it. Okay. So excellent question. It's always worth checking out. Is there a better one? But evenly distributed, if I can, and more electronegative atoms are carrying the negative charge. Do we know all those names for ionic characters and how they are represented? Oh, where was that? So at some point during the review, I talked about something being, there we go. I talked about percent ionic character, and I gave 5 different wordings for how this could be described. And the question is, do we actually need to know all 5 of those? So here is the truth. Here's the truth. Your exam is written by 5 different people. Whoever writes the question about polarity or about percent ionic character gets to pick the phrases that they use. And as long as everybody's used those phrases, they're fair game. For my classes, the 8 a.m. and the 9 a.m. sections, I used all 5 of these in class. I can tell you, those questions are not mine to write. I don't know which phrases that were used. So yes, you are responsible for all of these between the book and the notes. All 5 of these are ways to describe the same effect. So yes, you do need to know what all of these are, the fact that they are all describing the same general idea. Are we going to test you on all 5 of these? No, we're going to test you on at most 2 of them. But that's the hard part with one exam being written by 5 different people, is everybody gets to choose the language that they use. And as long as when all the instructors look at the exam, they know, hey, I talked about this with my students should be okay with describing that as a dipole moment. My students should be okay with describing that as partial charges with the little lowercase delta symbols that are there in green, then it goes through. So it's always a valid question to be like, do I actually need to know that? And in this case, for my students at least, that answer is yes, because I covered it. So when I look at the exam, all 5 of those are okay with me. Back to the questions. Okay. So we did effective nuclear charge, which we don't need to know. We looked at adding all the double bonds of phosphorus and why we do not like that one as much. We talked about all the different names for ionic characters and that you are responsible for those. This one, so going from empirical to molecular is just the closest whole number. So short answer to that is yes. Let's see if I can scroll back and find that. Oh gosh, make it small, make it small, make it small. So I did a very brief example. There it is. Because I was trying to think of all of the different ways we could do math in here. So this question up here begins in red. The empirical formula is CH3. The molecular mass is 30 grams per mole. What is the molecular formula? So this is keeping in mind that the 30 grams per mole is the total mass, and the unit that we have is CH3. So what we did is we found the mass of the CH3 unit, and then we went ahead and just set up a ratio with the 30 on the top, the 15 on the bottom to give us a factor, essentially, so that we could multiply our empirical formula to make it bigger. Because if these 2 numbers are not the same, then my empirical formula has too few atoms. If they're the same, then the empirical formula is the same as the molecular formula. But otherwise, this is usually done so that the empirical formula is a small version, the molecular formula is the big version, to figure out how much we need to multiply it by in order to get that. And yes, it should be a whole number, because your empirical formula is given as all in whole number ratios. So 1 carbon, 3 hydrogens, whole numbers. When we're looking for a molecular formula, we should still be in whole numbers. So we still expect to report a formula. So we still expect to report a certain number of atoms of carbon to a certain number of atoms of hydrogen. I should never see, see something like C 4.5 and hydrogen. I'm going to get the ratio wrong. 9.8, whatever. So this is not how we report molecules. So we never report molecules with decimals in here. They should always be whole numbers. So always whole numbers. So that's what those things should look like, whole number ratios. So yes, when you're going to go from empirical to molecular, the question was, are we just going to find that nearest whole number? Yes, yes, you are, because you've got to have whole numbers for this. Okay. So the last question, which I know was the first question, what are the rules for naming compounds and nomenclature as a whole? So the reason why I saved this one for last is because this is the longest. So for people who are already comfortable and familiar with nomenclature, I recommend that you either fast forward this part because it's in YouTube and you can play this at double speed, or you should X out of here and be like, I'm done, because this is this could take me a while. So first of all, this is all in your textbook. Your instructor should have given you resources in order to actually do all of this. But I will do a relatively quick version just to go ahead and say that I answered all the questions. So naming compounds and nomenclature. So first of all, whenever we talk about naming, and for those of you who are watching this, I'm basically going to recreate the flowchart that's in your textbook. I actually really like that flowchart, so I'm going to recreate the flowchart. So as far as naming goes, you got two basic options. You have ionic things and you have molecular things. So molecular things are going to be all nonmetals. And so when we look at a periodic table, there is one. Right here. I don't know why that error message is popping up 3 times. I swear it just wants me to do it twice. So when we say nonmetals, this particular periodic table is color-coded. Yours on the exam is in black and white. But what is happening here is you have things like carbon, phosphorus, selenium, iodine, radon, hydrogen. They're all nonmetals. There's actually a key down here to tell you that all the blue things are nonmetals. So all of those nonmetals, we're gonna name things like that. We're also gonna wind up including boron into the nonmetal set. Riker, buddy, you're okay. Sorry, it's my dog. He is not impressed that I am making a video instead of taking care of him. He's fine, by the way. He's already had breakfast. He's had some backyard time. He's doing fine. He just wishes we were back in bed. Okay, so molecular are all nonmetals. And for molecular compounds, we just name these with prefixes. So we use prefixes for these. So there are Greek prefixes. I will go ahead and grab that chart as well, just to show off the fact that there are 10 of them that you are responsible for. There they are, Greek prefixes, 1 through 10. So we are going to be using these for dealing with nonmetals. Now, there's only really one exception to worry about. So let's do a regular, normal looking one. So if I have something like P4O10, what happens is I need to tell the audience that, hey, I have a compound with 4 phosphorus and 10 oxygen. This is all molecular. They're all sharing electrons. So I should tell you what I have. So this becomes tetraphosphorus. Also, I know I was saying things about spelling. On the exam, y'all have a periodic table and all of the elements are on it. So you should be able to spell the word phosphorus because you can copy it down. So for those of you that are like, what about spelling? All you have to do is copy the word. If you had to memorize some of these spellings, we'd have different opinions. But since you have a periodic table in front of you for the exam, all you have to do is copy the word phosphorus. You can copy the word phosphorus. So this is tetraphosphorus. This is going to be decoxide. So we oftentimes drop one of the vowels in dealing with oxygen because otherwise things get weird quickly. But there's my compound to deal with all of my prefixes 4 and 10. Now there's exceptions to this, and then really the only exception is something that you've probably seen and heard before, which is where if the first element, there's only one of them, we just call this carbon dioxide. And we just call this one carbon monoxide. So this is decaoxide. I'll have to look that up. So realize that when there's only one element, we drop the prefix. So only one, we drop the prefix. That is nonmetals. So yes, you have to memorize this set of Greek prefixes. No, we will not give them to you. Yes, you have to have them memorized. You have probably seen them before in other ways, in other places. So a lot of these are prefixes that we've seen before in everyday life, like an octopus has 8 legs, a hexagon has 6 sides, a triceratops has 3 horns, things like that. On the other side, naming, ionic. So this is where things are put together with charges. So there are charges holding things together. Sorry about that. So there are 2 main sets in here. There are charges where there's only one charge option. And there's one where there are multiple charge options. What do I mean by that? Well, when we come over and look at the periodic table, some of these always only have one charge. Alkali metals, all +1. Alkali earth metals, always +2. And there are 4 elements you're responsible for. Zinc and cadmium, which are +2. Silver, which is +1. And aluminum, which is +3. So 2 columns, 4 additional elements that if you look at them, they actually do have an order to them. So they actually do go 1, 2, 3 on the periodic table. So they're not too bad, but those 4 elements are ones you're responsible for. So we're going to talk about the only one charge option first. So there's only one charge option. Then essentially, we're going to assume that people reading your formula have a periodic table. So if I grab something like magnesium and chlorine, actually, let me just grab these 2 elements off the periodic table, even though you only asked me about naming. So magnesium, I covered it up, but it is actually hanging out right here. It's where the magnesium is. There we go. So there's magnesium, and my chlorine is over here. So I know magnesium can only have a +2 charge. Chlorine can only have a -1 charge. All my nonmetals are stuck. My nonmetals didn't have any options of charges. I didn't cover that here, but they do. If you've never seen that one before, please go back through your notes because there's definitely diagrams of that to show off the fact that halogens -1, chalcogens -2. We don't call these, but they are picnictogens -3, carbon -4. So this compound would look like this. And to name this, all we do is we're going to name the metal, which again is hanging out on the periodic table. So you can absolutely spell magnesium correctly. And then we do have to change this part because just like we did for nonmetals, whereas the original element is chlorine, I-N-E, the new one is going to be chloride, I-D-E. So there's only one charge option. You just name them. That's it. When the anion gets IDE. If you have multiple charge options, so let's say we were doing, and now to actually have more information, cobalt, and let's go ahead and throw in a polyatomic anion. So essentially, I need to know about this anion so that I can know what to name the cobalt, because cobalt is hanging out right here, cobalt. So it's not a known one, it's in the unknown set. So it could have a whole bunch of different charges. So I have to tell my audience what the charge is on cobalt, but to do that, I need to know what the charge is on cobalt. So I need to know what the charge is on this thing. So nitrate is in fact a polyatomic ion. You need to memorize all your polyatomic ions that are in table 5.10 out of your textbook. But this is nitrate as a -1 charge. So therefore, since this is a -1 charge, my cobalt should be a +2 charge because it takes 2 of my nitrates to cancel out the positive charge on the cobalt. So therefore, when I go to name this, I'm going to name this cobalt parentheses without a space in between 2, and then the word nitrate. So if the charge is something where it could be a variety of different charges, you have to specify and tell your audience what the charge is. In order to do that, we just put the charge in Roman numerals. If you are not familiar with Roman numerals, the way they work is capital I is 1, then 2 of those is 2, 3 of those is 3, and then we start to do weird things because of V is 5. So to do 4, we actually subtract 1 from 5. So that's how that one works, is V is 5, and when you put the I in front of the V, in front is subtraction. After it is addition. So this is 6. So V followed by the I after is addition. And the whole notion that the orientation is all around the larger number. So basically you are focusing on the fact that V is a larger number 5 than the I, which is a 1. So that's the thing that kind of gets priority in this. Numbers keep going. I don't know that we would actually ever need this, but just since I started this whole mess, that's 7, that's 8. So you get to go all the way again to 3. And then when you need 9, we again are going to look at the fact that an X is 10. And so an I before the X is 9. Why things are like this would require a history lesson that I am not prepared to give. But this way, at least we've done Roman numerals. And actually with this, you can go up to quite a ways. But there's 1 through 10 in case you are unfamiliar with Roman numerals. So there are 3 other things in naming to mention ever so briefly, I guess 4. One of them I talked about earlier are common names. There are a grand total of 2 common names you are responsible for. It's this one, which is water, H2O is water, and NH3 as ammonia. So you are responsible for knowing these two formulas and these two names. The other one that I don't always think about this as common names, but there are a set that if we say something like hydrogen gas, we now mean H2 because there are 7 homonuclear diatomics that go with Brinkelhoff. Brinkelhoff is how I learned it. So it's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. And basically all of these look like this if they're hanging out. So the oxygen that we breathe in the air is O2. The nitrogen that we are also breathing in the air, just not helpful for our biology, is nitrogen. Well, actually, that is helpful for our biology, but whatever. It's helpful for our biology because humans don't do well if it's pure oxygen. For those of you wondering what I'm mumbling under my breath, humans do not do great with pure oxygen. Sometimes people call this the Magnificent Seven. So it's these here and then hydrogen. So or 7 star. I don't really know how that one works because in high school I was taught Brinkelhoff. So that's another thing. And then the other 2 things, there are acids, which I actually covered in the earlier video. So I'm not going to go back through the acids. I'm just going to remind you that there are binary acids and there are oxo acids. And I talked about how to name those in the video earlier. The last thing are hydrates. And this one is really not that bad. It just looks a little weird. Actually, I think this is supposed to be a 7. I'm trying to remember what the actual molecule is here. So it's got a part that we've already covered, which is dealing with elements. So my chlorine should have a -1 charge. My cobalt, therefore, has a +2 charge. So this is cobalt to chloride. And then I gotta name this thing. Well, that's a 7 and now water. So I am actually gonna name this then using my Greek prefixes. This is hepta. And then when you talk about water, we drink water, we stay hydrated. It's a hydrate. Ta-da! The notation's a little bit weird. We do use this dot in the middle, essentially because we are trying to describe that those waters are part of the formula, but they're not ionically bound. They're not covalently bound. They are hanging out in the crystal all together. So hydrates are a little bit strange because they can basically have specific waters in their structure. So this particular slide has an example on it that has copper 2 sulfate pentahydrate, and the pentahydrate is the blue one. So it can also be fairly pretty, but water's in the structure. Okay, so nomenclature, I did not go over acids again. I did talk about hydrates. I also didn't go back over polyatomics. I just mentioned them ever so briefly. I mentioned polyatomics earlier in the exam review, the fact that there's a list that you are responsible for. Here they are. So you are responsible for this list. Also, if you wanted somebody else to go over nomenclature with you, you have a couple options. One, you can go to peer tutoring and they can cover it with you. You can also check out whatever resources your instructor gave you to talk about nomenclature. And there was one that I was actually looking at this before the exam review to see how good it was. My YouTube search is probably not the best thing, but that's okay. Crash Course Chemistry nomenclature. So this video is a bit old, but this is, what was the one I did yesterday? Oh, there we go. How to speak chemistry in Crash Course Chemistry number 11. That's the one I want. I got confused because this one is number 44 is going into more organic things that we don't need. This one down here, how to speak chemistry and crash course chemistry number 11 would actually be useful to you. This is missing hydrates, but it does cover acids. So that does have so has a fair amount of good information, is actually missing hydrates, but aside from that, also useful information. So that is all of the questions that they gave me from the review. I know those are not necessarily all the questions that were asked, but they are doing their best to basically look through things that we either already talked about in the video, so that you can essentially go back, rewind, and take a look at that. So hopefully this helps. Your exam is Saturday at 10 a.m. So start studying, get ready. Good luck.